Hey guys, welcome back. Is this circle familiar to you? For those who don't know, this is a traction circle. Traction circle basically gives an idea of the forces that are acting on a tires. For example, if we are accelerating our vehicle, then there'll be longitudinal force, and hence the force will be on this longitudinal axis, and the same when we are braking, but in the opposite direction. During the When we are cornering, the tires will experience lateral force, and hence the forces will be shown on the lateral axis depending on the turn we are taking, for if it's right or left. Yeah, so that's basically a simple explanation of this traction circle. But now you can see there are two things over here: the ideal and the real traction circle. Talking about this, the real traction circle is not actually a circle but an oval. Now, what causes this difference? The fact that the coefficient of friction in this longitudinal direction and the lateral direction cannot be achieved at the same time. Now, if I rephrase my sentence, keeping it very simple, when we are riding a vehicle, let's say we are on a very straight road and we are driving a vehicle at full speed. Now, when we encounter a turn, we have to slow our vehicle down. That is, we need to enter the turn very slow so that we can exit fast. If not that, we can maintain the speed of the vehicle. We can have fast entry, but when we exit, we need to keep our vehicle slow. So that means this longitudinal force that our vehicle was experiencing, that our tires were experiencing on a straight path, cannot be converted 100% into lateral force when we take a turn. Because of this limitation, this difference arises, and hence the real traction circle is not actually a circle but an oval. But now you may ask that this oval is more on the longitudinal axis is bigger than the lateral axis in this real traction circle. So why is this so? Well, let's see that. Let us first consider a tire with a front view and a side view. When we run a vehicle on a straight road, there'll be circumferential force that will be acting, and when we take a turn, there'll be lateral force. Well, the direction can vary depending on the turn we are taking. So, as we can see, if the circumference of our tire is more than the width of the tire, hence if we go back to the traction circle, it can be easily understandable that the longitudinal force, that is this which is acting in this longitudinal direction, is more than the lateral force. And because of that, we have this such kind of oval. Now, I think you may have guessed right. This traction circle depends on the type of the tire too. Now, if there is a wide tire, the lateral force there will be more, and hence this oval can change. The size of this oval can change. So that was basically how this traction circle works, and how it can change depending on the size of the tires and the forces that are acting on the tires. To understand this concept more clearly, let us consider the racing lines of two drivers for a 90-degree turn, like I have shown over here. The blue line is for driver number 1 and the red for driver number 2. This dotted black line, we'll talk about that a little bit later. But first, let us talk about this coefficient of friction. As we know, there are two coefficients of frictions. The coefficient of friction for the longitudinal axis for the longitudinal forces, and the same for the lateral forces. Now, the law says that, as we have talked about it earlier, that the maximum coefficient of frictions for forces on both the axes cannot be achieved at the same time. Let us understand this with the line of race. Here for the driver number 1, he goes for the early apex, or here we can clearly see that he does not, he chooses for the acceleration, hits the apex, then takes a turn. So what he is doing is, till here, as you can see, the path is somewhat straight. The tire is facing the longitudinal forces. Okay, till now there were the longitudinal forces acting on the tire, and he had the maximum coefficient of friction for that. But then he had to take the turn. So what he is doing is, now he requires the maximum coefficient of friction for the maximum coefficient of friction for the forces on the lateral axis. Because he is taking the turn, the lateral forces will be acting on his tires, and hence he'll require the maximum amount of the friction. Quite understandable. So he'll have to brake in order to achieve this maximum, the maximum value of this friction, the lateral on that on the lateral axis, and he need to lose somewhat coefficient of friction for the forces on the longitudinal axis. And hence we can say that all the forces from the longitudinal axis are getting transferred to the lateral axis. And again, after taking the turn, he chooses for the acceleration, and hence he exits the turn, exits the curve. Basically, he goes for the fast entry and slow exit. He's obeying the law because here, as he's applying the brakes, he's going for as he's applying the brakes, he and as we have discussed earlier that both these maximum values cannot be achieved at the same time. He's going for one maximum value at a time. Talking about driver number 2, the case is the same, just the difference is he applies the brake earlier, takes a turn. In other words, he chooses for the maximum coefficient of friction for the forces on the lateral axis earlier than the driver number 1. So yeah, he takes a turn, applies the brakes, and then goes for full acceleration, hits the apex, and exits the curve. So slower entry and fast exit. Now talking about this dotted lines. Here we can see the driver is going for the acceleration. There is acceleration over here. He does not apply brakes and goes for the fast exit. Yeah, fast entry and fast exit. Now I think you might have guessed right till now. There is no, he is trying to achieve both the maximum values of he is trying to achieve the maximum values of both these frictions, coefficient of frictions at the same time, which is not possible. So hence this line is just an ideal line. If a driver tries to go for this line, then there is the most he is most likely to lose the stability of the vehicle. So I hope till now everything was clear about this racing line and how these maximum values of these coefficient of frictions cannot be achieved at the same time. Now taking this thing to traction of circle over here, the first case, driver number 1, he goes for the acceleration initially like I have shown over here, the straight line. So the vector force will be in the direction, the positive direction of on the longitudinal axis. This is the longitudinal axis and this is the lateral one. So now acceleration, so straight line, and then while taking the turn he slows down the vehicle, and hence the curve will, and yeah, and also the longitudinal forces are getting, the forces on the longitudinal axis, I'm sorry, the forces on the longitudinal axis are getting transferred on the lateral axis. So hence the curve will go towards the side, and the curve will look somewhat like this. The entire curve on the direction of circle for this racing line will look somewhat like this. And now the same for the driver number 2. Yeah, he applies the brakes first over here, so the line will be somewhat opposite. It will go down as deceleration, then the force is getting transferred on the lateral axis, constant speed somewhat, yeah, and then goes for the full acceleration on the exit of the curve. So yeah, for driver 2, slow exit, slow entry, and fast exit. So this is how, when one follows this law, then his vehicle will be stable, and his the traction that is available will be within this circle, within the limit, and hence there will be no problem while taking the turn. So this was all about the traction circle and the relation of the racing line with this traction circle. Now, if you have any doubt regarding this topic, this was a little bit complicated topic, and I tried to relate this with the practical situation. So, if you have any doubt, just feel free to mention it below in the comment section. And thank you for watching. I'll see you guys in the next video.